Good afternoon, everybody. Thank you for coming to today's lecture. It's really a great honor to have with us Professor Alberto Sangiovanni Vincentelli. It's as you most of you already know, if not all, he's one of the top researchers in our area, and it's really a great honor to have him here in Cyprus and at the University of Cyprus. So he asked me not to say too much, but I have to say something. And Professor Sangiovanni is a chair professor of electrical engineering and computer science at the University of California at Berkeley. He's the author of over 1,000 papers, 19 books, and 3 patents in the area of design tools and methodologies, large-scale systems, embedded systems, hybrid system, and AI. Just to give you an indication, his H index is more than 100, 128, which, I don't know many people that has this. I didn't know H index go beyond the 100. So anyway, so it's high. In addition to all his academic achievements, he has also been heavily involved in industry and the development of new companies. He's the co-founder of Cadence and Synopsys, which are 2 of the leading companies in the area of electronic design automation. He's in the board of many high-profile companies, and he has direct access to some of the biggest names in industry in the US and in Europe. I just wanted to also say that he's a fellow of the IEEE and a fellow of AACM, but also a member of the National Academy of Engineering, and also a member of the American Academy of Arts and Sciences since 2004. And he has received honorary doctorates from many universities, including University of Alberto in Denmark, KTH in Sweden, in Poland, and also, of course, in his home country, or the University of Rome in Italy. So it's really a great honor to have him here today with us, and he will talk about a very timely topic, and I'm sure he has a strong opinion one way or the other, which is going to let us know. Thank you very much, Alberto.
Thank you, Mario. Yes, indeed, I have some strong opinions about things, and at the same time, all I can afford to say what I think, so I don't have to be promoted anymore. I think they reached the ceiling, no more. Okay, so now let me go about what they're doing. No. Okay. Great. So this is the outline of my presentation. So I would start with design principle. It's something that I always start with, because I think that design is one of the most wonderful activity that an engineer is doing. Actually, it's all about engineering. Design is engineering. And then I would like to give a very quick overview of where we have been going in the area of integrated circuits. Now, you may have known now that the area of integrated circuits is considered to be possibly the most critical one right now in the industrial framework. So much so that the United States is putting down about $50 billion of investment in semiconductors. The European community, 54 billion. China just announced 50 billion again, and Japan and so on. So every single country, including Italy, 4.5 billion. So everybody is investing in semiconductors. The reason is, as we will see, that we can even think about artificial intelligence without having the supporting hardware that runs AI. And so that's the reason why it's so important. And this also is something that I strongly believe, is that when you think about electronics and think about design, you cannot diverge software and hardware. are coming more and more together, right? So for a while, it was completely separated. Now, in the latest 10 years or so, it's going back together. And we see, for example, for the GPUs and the algorithm for artificial intelligence, you have to take into consideration what is the platform that you run your algorithms on. Not for everything, but for most of the important things, it's very important that you do that. Then we'll look a little bit into cyber physical system. What are the choices in cyber physical system that we have to face, and what are the design problems that we have to face? And then we'll go into the meat of the presentation today, which says, okay, how does AI fit in all of this? And I would like to start that part of the presentation giving definitions. After all, you know, we are engineers, so I'm sick and tired to look at the articles where everyone is assuming that people know what AI is and what machine learning is and so on. And sometimes people talk just nonsense. So we got to make sure that we are talking about the same things, or we understand where we are. So we're looking at some of the trends. And of course, this one is not a lecture on AI, but we'll have to see what are the trends and what is the big revolution that has been happening in the past 4 or 5 years is about the introduction of generative AI and large language model. How does that fit into the design framework? And then I would like to give one example that I got to know directly, and we'll see why and how, which is AlphaFold 2. That's probably the best application of AI technology in science. And then we will look at the simulation-based verification. Now, this is a big topic, verification. So we know that AI is a statistical technique, and as any other statistical technique, you know what you know, and you don't know what you don't know. And so you have to be careful, because if you put autonomy, for example, autonomous vehicles, autonomous warplanes and all that, we have to be extremely careful that we don't deviate from what the object's supposed to do. And so we have to verify. And verifying something that is inside a significant block of AI or machine learning is a very tough proposition. So in Berkeley, together with my friend and colleague Sangiovanni, we are running a group that is looking at how you verify AI-based systems. And then we'll look at where and why you should use some of this technology in design. And it does have a strong position in design. And actually, design is probably, if you do it the right way, is probably the safest application of AI that you can imagine. So we'll look into that. And then finally, I'll give you some of the consideration that I have made over my research journey. So now, where did I start and why did I get into design? So that's the time when I got my degree, okay, 1971. Okay, 1971, there was no large integrated circuit. The large integrated circuit was the Intel 8008, which was 3,500 transistors. That's it. So do you know how many transistors is the biggest chip today? Well, yes.
DDM3?
No.
Oh no, NVIDIA on the
NVIDIA Blackboard. So how many?
Some trillion.
208 billion. I mean, trillion is the parameters, but in terms of transistors, we are more than 200 billion transistors from 3,500. Okay, that's my last, right? 3,500, 200 billion. Anyway, so we have magnetic core memories. I bet that half of you don't even know what is a magnetic core memory. But we have that, and we have a very nice interactive environment using punch cards to put the instruction into a computer. And well, we managed to do something interesting because we started design chips that became over the year more and more complex. So this is the history of microprocessor, if you like, in one slide. And so the 404, then the 8086, then the 8286, and you can see that there is some pattern that is developing here, which is a key in the principles of design. So anyone looks at this and can you see something developing? It's order, right? It's in the first chip that you see up there. Let's see if this thing works. Well, the chip up here is the Intel 404. It's like you have a spaghetti bowl and then you throw it on the stove. And so it's the transistor. After you do that, that's you get the design of this chip. Now in the 8286, you start seeing some order. Still some spaghetti there, but fewer spaghetti. And then fast forward, we go to the 386. And that is, in my opinion, not because I put my hands on it, but you see, it's much more regular. The design regularity is very clear. The patterns are very clear. And it's, in some sense, it's also aesthetically pleasing. In some sense, design also goes with simplicity and elegance. So a good design is elegant and simple. Yeah. So that's one of the KPIs that we would like to look at. So anyway, so we, why am I saying that I put my hands on? Because I was able to convince the Intel management that this was the only way to be able to design a chip that was so much bigger than what they ever did. And so they came actually to my office saying, well, we're never going to be able to design things in 2 years. So can you help us? And we understand that you publish these papers about design automation. So can you tell us how you do that? And the first thing I told them is that regularize your design, otherwise automation is not possible. Okay, so in fact, that's me, believe it or not, a few years ago. And some of you may recognize the guy in your parent lab. That is Pat Kelsen, the present CEO of Intel. And at that time was a young engineer, and we were working together on the 386. So pretty interesting because the Intel guys tried to convince the world that indeed that was the path to go. Simplicity, regularity, use of tools. Because remember that before that, most of the design activity in chips were manual. They were all hand design. So this was really something fun. So, okay. So in some sense, what I was trying to do, and when I came to the United States, I mean, we are in Europe, right? So we know what European stands for, but, and the role of engineering in, in our culture, but United States and in general in the UK and other Anglo-Saxon countries, the engineer is the guy who fixes your toilet when it doesn't work, right, in the hotel. Or is the guy who runs the train. And that was the perception of the Anglo-Saxon world, that an engineer is a guy with a screwdriver. Now, is that the same in Europe? Not quite. In Greece, certainly not. In Italy, certainly not. In France, less and less. I mean, France was the domain where École Polytechnique was considered to be the very best school. Okay, so that is the angle that you would like to take. And so one of the things that you have to do in the Anglo-Saxon countries is to make them understand that there is science in engineering, and that is not a matter of putting together something and then hope for the best, right? So pretty much the design that I've seen when I went there were pretty much like Palafit, so that we're going to collapse in 5 years, nothing left. But of course, again, I think that you will relate to this. This one is Segesta, is one of my favorite place ever. This one is more than 2,000 years. And it's a wonderful piece of art. Still there, still standing, nothing broke. And so that is what we should strive for, right? Something that stands for thousands of years, hopefully. Right? So, well, once we start looking at that, we started trying to distill what was important. So how did we cope with complexity? Well, first of all, abstractions. An abstraction is a key of engineering, in my opinion. An abstraction is when you try to eliminate details that are not important for the goals that you want to achieve. And so abstraction is a key concept in all engineering. But once you abstract things, then you can derive tools, because abstraction are simplification. Remember, simple and elegant. And so we have tools. Now, the combination of abstraction and tools for methodology. And methodology is what we call freedom from choice. So you're giving boundaries to the designer. So we saw in the 386 that you had these nice line things, right? And then we say that if you did use that regular structure, then you can use tools, and then you can get designs which are correct, like in fast time and a little cost. So that is the key point, is methodologies. Now, if you look at some of the AI principles people use, right? So you try to be general, like things about large language models and the like, ChatGPT and so on. It answers any question, right? Why? Because it's been training on everything that you find in the internet. But sometimes it hallucinates because it cannot get everything right, of course. Now, if you limit the space in which you are asking questions, then you can get so much better performance. Freedom from choice. So if you leave anything completely free, then you are bound not to get the right answer. Is absolutely for sure. So you have to limit what you do in exchange for gaining verified results and optimal results. Okay, now moving right along, the history of abstraction, that's what happened. And what I was part for is defining this abstraction in chip design. And so we went from geometrical objects that were the transistors all the way to large blocks. And this is where we are today, also called IP blocks. So you design by putting together Lego blocks, essentially. Okay? So big Lego blocks. Now, that is a very good way of making your chip faster and better and possibly correct, because you already designed pieces that you are verifying. So when you put it together, if you do it in the right way, what comes out is correct by construction, and so it takes much less time to do it. Now, unfortunately, this is pretty much where we are. Okay, so this is the highest level of abstraction that is available today, but it's still a big step forward, so much so that we can build monster chips, right? This one is called the Apple A11 Bionic. It's 4.3 billion transistors. It's a lot of operation. It's what you get in your cell phones, okay? Now, Apple was the first time that they designed integrated circuit. Before, they were just assembling integrated circuit in boards, and then they packaged and they made the iPhone, the iPod, and everything else, the Mac computer, and so on. So this is the trend. Now, Tesla has designed its own chip. Google has designed its own chip. Amazon is designing its own chip. Why? Well, because you get much leverage, remember what I said at the beginning, from the hardware to speed up what you do, right? And all these companies that I mentioned are for the hyperscaler. So there are people that do a lot of money out of this, and of course, you know, things like the cloud needs a lot of computing power, let alone artificial intelligence. So there is advantage into being able to design your own chip. Now, this is pretty intense to say, because it is difficult to design chips. Except that we found a way, right? By increasing the layer of abstraction, building these libraries of components. And by doing so, we are enabling or empowering an entire new generation of systems. Because now we go to the point that you can conceive a system, and you can conceive a system all the way from the specification another, go back to the future, right? Back to the future, because in the old times, that's what everybody was doing. Then they abandoned it because it was too expensive. People didn't know how to design chips, and we're back to the point where people design systems together. Now, say this, let's take a look then at the physical system. And again, I'm going to stress the fact that inside the physical system, the key decision is indeed about the architecture. So what we put together to obtain the final version of what you are designing. So a typical example of the cyber-physical system is an autonomous car. It's the ultimate example of the cyber-physical system. Now, when I design an autonomous vehicle, what do I need to do? First of all, it's a vehicle, so I need mechanics, right? The mechanical components have to be designed. But then I also have to design the brain, the cyber part of the system, that is going to make the car do what you want to do. Now, next step is to put the brain, big brain, in the car and let the car go alone. Are we there yet? Yes, of course. You can find cars in San Francisco that go around and drive pretty well. Definitely better than 90% of the humans, but not 100% of the humans. And this is where the problem lies. Right? Because everybody is expecting that if you have an autonomous whatever, they are not going to have any problem. Now, that is not going to happen. I can guarantee you. No matter what, no matter how good you are in designing, no matter how good you are in developing algorithms, you're always going to have a situation where the system is going to fail. But give me the number of people who die every year on the road because human die. Rough number? More than 1 million. 1 million people die every year. Right? And so everybody is so concerned about the fact that sometimes an autonomous car crashes. Of course, we don't want to kill people, but the fact that it crashes is in the noise, right? So if you say that the number of accidents has to be limited by X, that's all you can say. You cannot say that it has to be 0, right? Even the planes were, planes, right? So if you look at the way in which the systems are designed inside the plane, is that the probability that they break is less than a very small quantity, but not 0. So there is always something that may go wrong, and you try to keep that something as small as possible. That's the optic that you have to take when you think about autonomy, that you cannot eliminate all the possible accidents, you have to limit them. And so anyway, so you got all this wonderful system. There are another important, and you say, what is cyber physical in that? But the server part is hyperscaler, we say before. Is that the cyber physical system? Yes, it is. Why? Because the other right? The racks are mechanical system after all, there is a structure. But most importantly, one of the key issues when you design a server farm is heat dissipation, right? So cooling, and you want to also be able to design the components that go into the servers in such a way that they consume as little power as possible. As little as possible doesn't mean 0, okay? So if they consume a lot, even if you try to limit it, and so you have to disperse the heat. And there is a lot of science that goes into finding the positioning of the computer in the server farm and the positioning of the fan and the cooling system to make it as efficient as possible. And so, in fact, there is a company that has as their goal the design of cooling system for server farms. And in fact, Cadence Boyd, it is just to show you that the cyber-physical nature of anything that you design is there, right? So you have a computer server, and you say, well, it's computer, so that's definitely cyber. No, it's also a lot of physical in there, especially when the power comes in. Now you have a variety also of choices when it comes to the electronics that you are going to use. So the point is that how do you choose between all this freedom, right? Remember, I want to have freedom from choice, but on the other hand, I want to leverage what technology offers. So I have the possibility of doing single chip 3D IC packaging, printed circuit board, flexible board, you name it, right? So there are infinite ways in which I can skin the cat. So one of the things that I've been known for in the past years is that I kind of figure out a methodology to be able to take the system specifications and then try to find what is the best combination of IP blocks, in this case can be big blocks, to satisfy the requirement you have at all. Now, this extends also to mechanical part. If you look at Volkswagen, they have 3 basic mechanical platforms for all their models. And there are tens of models of cars in Volkswagen, but they all originate by the same set of components that you put together in an appropriate way, which is exactly what we have done in electronics with the big reusable blocks. So the entire world, no matter what is designed, is going to work that direction. Last but not least, I don't know if you have seen synthetic biology. Synthetic biology is the science of designing bacteria that don't exist in life, right? So invented bacteria. And how do they do that? By putting together components. And what are these components? Strands of DNA. So you build things by combining smaller pieces in such a way that the combination is performing what you ask it to perform. So no matter if it is mechanical, no matter if it is a physical system, no matter if it is biology, no matter if it is a computer program, the principles are always there. Library of components, assembly of library of components, and choice of the interfaces that you have to use in order to combine these pieces. Now, there is an interesting phenomenon that we are witnessing in the past years, the generation of an immense quantity of data. So if we look at every second, we generate trillions, terabytes of data. And by now, probably petabytes. This data is about 5 years ago. So by now, you have petabytes that are created every minute, right? So, well, what do you do with all this data that are generated? 99%, you take the data and throw it away. Now, you know that there's been a big debate about who owns the data. And oh boy, these bad companies that are stealing our data and then they are reselling this data. Not really clear what you can do with this data, and not really clear why you should care so much about the use of data that are immaterial, right? So, for example, how many coffee you drink a day? I mean, how many people would be so interested in that? But if you are a guy who's making coffee, he wants to know more or less how many coffee are being drank over a day in the world so that he can tune up his production. So for me, his value is 0. For him, his value because it's aggregated, right? So, I mean, it's normal. I mean, it's making life of everybody better because I can get coffee at lower cost and possibly better quality. So the issue of privacy, in my opinion, has gone beyond what is reasonable, to a point that sometimes I really get upset when you say, are you willing cookies? I don't know. Tick, 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 tick. Are you willing? At some point I say, yes, take all my data. I don't give a damn, right? Because the time that I spend to say no is more than what I spend doing what I need to do, right? So don't care, do whatever. I have no secrets that I want to maintain. But on the other hand, since all this data is available anyway, what is a good use of all this data? Of course, data means knowledge, they say, but unstructured knowledge. It would be nice if we have a way of putting together this data so that we can do something intelligent, right? So how do you do that? Well, guess what? I mean, we have been doing this since the invention, since the Egyptians, right? I mean, you are a physical phenomena, and we're trying to find the relationship between events. That's what it is. So we have this data, so observation, and want to find out if there is a correlation, or better, causation between certain effects, certain other effects. So how did we do this over the years? Two ways. Intelligently, so Newton, Galileo, whatever. Then they were trying, Einstein, they were trying to find the laws. So the physics that is behind it, so that they could predict, given a particular situation, what the outcome would be. The other way, especially when you have terabytes of data, it's very difficult to try to figure out what is the law behind it. Don't give up, but it's difficult. And so the other way that everybody has used is to use approximation. And approximation, you have input-output maps, and you want to find a function that fits the data, right? And that's an approximation theory. Well, I mean, in the case of, for example, control theory, we have been doing this for ages, right? Identification, right? So you have a system you don't know, you try to identify it. But in order to identify a system, what do you need? You need an hypothesis of what is a good function that will try to approximate something I don't know. You know, this is the problem with what I was saying before, is that you know what you know, you don't know what you don't know. And so it's always a guess somewhere, right? So guess what machine learning is all about? It's trying to find a function that fits the data. Okay? No magic there. That's what it is. And this is the way in which you're trying to predict what will happen if a certain input pattern comes in. Now, there are some things that you can try to guess. Well, I mean, a million times if I drop this thing and goes down, then it's likely that if I take another object and let it go down, it's going to go down. Are we sure of that? Not even. But in principle, we know that more or less this is going to happen. But, okay, so we know that there was a basketball game 2 days ago, right? Olympiacos against Real Madrid. And it was fanatic. Sorry. My data corrupted. So anyway, so how many people would guess that Panacea would have won? Very few, right? So, I mean, the facts, of course, everybody, yeah, but in principle, the data will tell us that probably the other team would have won, right? But yet, no. So, that's the point. How can you predict the future of something that you don't know the law of? Right? So, the law of who is going to win a soccer or basketball, we don't know. Otherwise, we'll be all rich, right? And go out and have a nice bottle of wine. So there are certain things that you try to use in an improper way. So you're trying to predict the future when this future has no law, right? So who's going to win the football game, right? So that kind of stuff that we always have to keep present when you think about artificial intelligence. You know? So the big reason why AI is so hot today is because we have an immense compute power, and it's getting larger and larger, and we have an immense amount of data. We never had the two combined together. So is AI machine learning new? Not quite. Okay, so let's look at a little history. And before doing that, let's define things. So artificial intelligence. So you notice that in any paper on newspaper in the world, AI and machine learning are the same thing, and they are not. So if you look at the actual definition of artificial intelligence, is the theory and development of computer systems able to perform tasks that normally require humans. Okay? Now, what did I do all my life? I try to automate what? Design of integrated circuits. That's artificial intelligence, right? Because it's a task that was performed by humans and now it's performed by computers. So any automation is really artificial intelligence. That's it. anything which is an automation of something is replacing a human, sometimes worse, sometimes better, most of the time better, if you have the good algorithms and the like. And that is the reason why cadence is not now are worth $160 billion, because we do things better than humans. So with automation. So artificial intelligence contains all engineering. Okay, so that's it. Now we look at machine learning is a subset of artificial intelligence. In what sense? Because machine learning, if we use the definition of Michael Jordan, a very good friend of mine, colleague at Berkeley, who is considered to be the most important scientist in machine learning, are the algorithms and supporting theory for making predictions and decisions under uncertainty based on observed data. This is what we just said before, right? This is it. This is what machine learning is all about. Okay, no magic, no nothing, but it is a very important in general topic. So in some sense, the good thing that the amount of data and the amount of computing brought to bear is the fact that mathematics and statistics have become a very central discipline. And so if you look at the courses that we do in Berkeley, statistics and mathematics are getting back into a major attention, because if you want to do machine learning or anything like this with congruent size, so with some degree of intelligence, you've got to know the foundation. And the foundation, physics, mathematics, biology, statistics. That is, these are the foundations that we need to work with. So then artificial intelligence is generic, right? So all engineering is artificial intelligence, fine. Machine learning is a subset of that, and it's very precise what it does. And then there is a subset of a subset, which is called deep learning. Now, what is the difference between machine learning and deep learning? Well, deep learning is assuming a specific form of the function. Remember the approximation? We said we have to choose some function that we need to fit. So in some sense, you can even imagine that you have a learning, it could be Taylor series, you know, as an approximation, right? Isn't it? Now, Fourier series, approximation. Polynomial, approximation. And we know a general approximation theorem, Weierstrass theorem, that says that over a limited interval, you can approximate to any degree a function is given by point, right? And so that there are some people in machine learning, when they talk about neural network, you say, oh my God, neural network can approximate any function. Oh, really? I kind of learned this when I was a kid, right? When I was in high school. Come on, guys, why is that here? What is so fantastic about it? You can approximate using any base function you like. So deep learning is based on neural networks, right? So fine. And so let's look at the AI in history. So the first kind of work was started in 1950. Now, if you look at, you know, I've been not 1950, but I've been around since 1970. So I've seen all of this, right? So in fact, we saw that artificial intelligence got a peak of very large interest, and then it went down, boom. And then it went up again, and then down, boom. And why down? Because when you start preaching that, like a shaman, that this is a new religion, right? And neural networks are going to solve the worst problem because they're like the human brain. Oh, yes. Okay, anyway. Then, of course, you're going to crash, right? And that's what happened, right? So, interesting enough, I did write papers in the 80s about neural networks. Sure, I was part of the people who were interested in that. So what was I trying to find? I was trying to find bounds or limits where I could say that this approximates the neural network would give me an answer within a particular bounds. Okay, no hope there. So there was the AI Winter 2, and now is a big explosion. The big explosion is again due to the fact that we have lots of computational power and lots of data. Why lots of data? The more data you have, the better it is to try to guess what the function you're trying to approximate. You got to be careful because sometimes the data are too many, so you run the risk of overfitting, right, the data. And the prediction capability goes down the drain because you overfit the data. So new input doesn't give you the right answer. Second, the data may be corrupted. And remember that since this is an approximation domain, if you give bad data, what do you get at the output? Garbage out, right? So when people talk, oh my God, machine learning is biased. There is a bad guy behind, right? It's Daniel, right? No, it's bad data, okay? So bad data means that if you have a limited population of data, you may end up, I don't know how many women are here, but it's a minority. Then I can conclude that people who are interested in seminars about AI are men mostly, right? Why? Because this is the data. This is the data. Is that a reasonable conclusion? No. Why? Because we have a limited set of data, and this data doesn't explain the phenomenon. It goes back centuries, right? So that is the problem of bias of machine learning and all that. Okay. Now, machine learning then, same story. Machine learning started way early. So we're talking about 1958. I remember the Rosenblatt perceptor machine. And they were like discrete components, right? So it would look like a computer. And then you had all variations of on the idea that you could build a very nice approximation function based on a very simplified model on how the brain works, the neurons, right? Now, if you ask anyone who is a neurologist and you say, well, does this thing mimic the way in which the brain works? It's going to kick your ass. I mean, big time. And say, no, not the way. Neurons are so damn complicated, and there is not a single neuron. There are all kinds of different type of neurons that do different computation, not just the sum of the weighted sum of input and then the output is a spike, 0, 1. No, oh no, it's so much more complicated. The key point that we are trying to use in deep learning is essentially the structure, the multi-layer structure. That's the key point, right? Instead of having a flat computation, you've got many layers. And that, in my opinion, is the real critical aspect of learning. And in particular, deep learning means you've got many layers, right? Deep, right? Many layers. Now, do we have a proof that the multi-layer is better than any other multi-layer SQL node, any better than any other function node? And why do people use it? Because it's simple. It's simple to understand the data structure, and it's simple to use. Now, if you look at the history of neural networks, when I started looking at neural networks, what was the node? You know, in general, you have these nodes that are connected together. This is the reason why it's called connectionism, because there are components connected together. Now, the node was a sigmoid. There was no linear function, and where it was 0, and when the input were below a certain threshold, and the stuff lays out, and then you saturate. Now, what is the most used node today? It's much simpler. It's constant and then linear. It's called ReLU. And why is that? Simpler to compute. It's no linear, okay, but mildly linear. And then you can get by computing the input output of the node by linear functions, right? Sum of products. And then you say, wow, what is so magic about sum of products? Well, it so happens that if you do, for example, computation to render an image on your screen, what do? You multiply matrices by vectors, right? And so that is a very defined digital processing function. Right? And guess what? There was a company way back that was called NVIDIA. Now, what did NVIDIA do? It did GPUs. What are GPUs? Graphical processing unit. What they were doing, sum of products really well, really fast. Lots of power, but really well, really fast. Okay. Now, here comes neural network, right? What is the basic calculation in the node? You have a set of inputs that you have to multiply by the weight, and then you have to sum them up. Sum of product. Oh, it's the same thing as rendering an image on the screen. Oh, NVIDIA. How lucky can you be? You are sitting on something that was used for years and years and years, and all of a sudden it's the basic unit for doing computation for neural net. You see the combination of hardware and the algorithm? Okay, great. So there you have it, right? So NVIDIA is $2.5 trillion company. Okay. Did they design this thing having in mind? No. So that's where the luck comes in. Okay? So they're just sitting on a pot of gold ready to be discovered. 2.5 trillion. Not bad at all. I'm very happy about my company, but you know, it's 2 or 3 orders of magnitude bigger. By luck, you know. What can I say? But besides the joke, the point that I want to stress is also another thing. Now, have you seen the latest development of the node function? Int 8, for example. What is int 8? Nobody knows. Okay. So, for example, in the old times, you were using floating point, some products of floating point things, right? Int 8 is 8-bit integer, right? 8-bit integers. Now, if you are looking for mathematical calculation, that's the crap of the crap of the crap of the crap. You can't get anything right. Why integer 8 is so cool now? And then some people say, no, why not integer 4? And then now all of a sudden, why not Boolean? Right? No, well, it's simpler. But why doesn't it matter? Because it's the layers that matter. It's not the single function of the node. So we should let you understand that is the connection pattern of the architecture that matters, not so much what the node does. And actually, there are some people who claim that the garbage, the worst garbage that you can put in the node, the better it is. Right? So like 0, 1. Right? So if you look at the mathematics, if you're trying to approximate a continuous function, 0 and 1 ain't going to happen. But yet you can do something with that architecture. Reason being is layer. So is there a theory of that? I'm not sure. I didn't find it. So I'm trying to look into it to see if there is something that I can do. So here it is. So that's some products. So you have different ways and you get different computation, of course, because they have to with the functions of the way. So when you approximate the function with a neural network, what do you need to do? You need to find the way. And so the whole training issue is that how do I find the weights in such a way that the input-output relationship are maintained, are the ones that I give to the mathematical model as a training set. Then I have a test set to check if indeed it generalizes to things that the model has not seen before, right? So, but that's what it is. So, then I have to have an algorithm that decides what the weights are given this input-output relation. Now, how do you do that? Reinforcement learning, backpropagation is all about determining the weights. Now, if you look at the, for example, backpropagation, it is one step of the gradient-based method, which is the basic optimization technique that you use. Is this a linear function? No, it is not. Is it a convex function? No, it is not. We know that gradient-based methodology gives you the optimum if indeed the function is convex. If it is not, we go someplace that may be a local minimum, But even then, back propagation is an approximation of the gradient technique. It doesn't get you even to a local minimum. So how come back propagation, reinforcement learning, and all this nice stuff works? It's the same thing as a node, right? So it's not important. Just get something, right? And so that gives me the feeling that there is a lot more to be got in the basic mathematical model. Always remembering that you know what you know, you don't know what you don't know. So it's an approximation, but even in that domain approximation, can we do something better than what we have been doing so far? So machine learning and approximation. So a deep learning architecture is a multi-layer function with many parameters. The parameters are determined by fitting a training set, and then you test it with the test. Okay, so this is a machine learning one word. Now, I told you about NVIDIA, and everybody's very happy because NVIDIA does computation that are useful to train and to deploy a deep neural network. But here is a combination again of the algorithm and the hardware. So this one is Tesla. This is the Tesla chip. Now Tesla is supposed to be a car company, right? So what the heck does the car company do by designing chips? Well, guess what? This chip is actually what is the real core of Tesla, but it's not so much because this chip has two NPU. What is an NPU? Is neural processing unit. And what is a neural processing unit? Sum of products. Okay, but you cannot call it GPU, otherwise you get sued by NVIDIA. GPU is mine. Don't touch it, right? But same thing. Now, why is this a revolution? Because now you have a huge chip that can do all kinds of computation, not only neural network, all kinds of other stuff, right? And so if you look today, your car, go and open your hood and look inside your car. There are tons of printed circuit boards full of processing units and all that. So there are more than 100 processors in your car. Now with this guy, how many processors do you need? One. Keep it simple and stupid, just one. Now, the trend always in automotive has always been putting more stuff, more units that do computation. So it's a revolution. No need for that. Now, you know how many kilometers of wire are in your car? And it's copper, so it's expensive, right? There are more than 3 kilometers of wire in your car because you need to connect up all this stuff, right? If you have a single chip, how many kilometers? Maybe 20 meters. So it's a huge simplification. So it's not so much because of artificial intelligence or because Tesla is an electrical car, so big deal. How many years have you seen electrical cars? If you are as old as I am, since 1980, you already have electrical cars. The key point is that the Tesla is an electronic system dressed like a car, okay? So there is a revolution that is taking place there. This is an NVIDIA Blackwell, so 208 billion transistor. By the way, it's beautiful to look at, right? So if you look at the layout of this chip, it's really good. And this one costs a ton of money. And costs a ton of money because it's complicated to design, it's complicated to manufacture, but especially because there are many people who want it. You know, the law of demand and offer, so it's very unbalanced. So that's the reason why NVIDIA is 2.5 trillion, because they print money. There's a lot of demand, and so the prices are very high. The margins are incredible. And so everybody plus his brother now is trying to copy NVIDIA. So we are going to have a glut of AI-based chips, so, which is bad from one side, but it's good from the other side because the prices are going down, architecture are going to be different. Maybe algorithms inspired by new architectures are going to come up. So we are at the beginning of yet another revolution, if you like. Okay, limitation and trends. So machine learning and approximation. This is a red bar, right? Is there any guarantee that this function will approximate the real function? No guarantee. Okay, so if you want to have a autonomous vehicle that is going with neural networks, deep learning, and all that, to make decision about where to drive, how to steer, and all that, you're out of luck. I mean, you cannot guarantee that it's going to work. So it's just empirical evidence that this is going to work or not. So in fact, there is a growing use of artificial intelligence in automobiles, so the dollar amount is impressive. You know, Tesla is betting their future on this. Right? So Elon Musk is gone public by saying this is going to be the future of my company. Okay? So there is a lot of money behind it, but there is also a lot of worries about, you know, what can we guarantee? So growing concerns about safety. And in fact, the neural network can be easily fooled, which is bad because you can have hackers that can really cause accidents of all kinds of types. All right. So in fact, this one is a famous paper by Stanford, unfortunately, but here you go. And so this is the, the way in which you can fool a neural network. You see that gray abstract picture is being mistaken by AlexNet, which is a famous architecture for image recognition, as being a king penguin. Now, I know that any one of us, unless it's blind, will recognize that that is not a king penguin. But the AI module that does image recognition, we say that is a king penguin. And why is that? Because you are recognizing images in fact now a bit better by looking at pixels. And so if you look at such a small grain of complexity, then of course you tend to you give a pixel that is not expected to be in that position, and the deep learning network is going to give you the wrong answer. That is the big problem. Now, how many of you have seen CAPTCHA, right? And everybody, right? So when you say type this letter that you see, or recognize this a bicycle or something like that. Now, if you look at the images, especially for a CAPTCHA that are a bit more sophisticated, what do you see? Are they very crisp images? No, they are blurry. Right? Why blurry is so important? Because of the pixel-based image recognition. So the idea is to pull AI-based image recognition so that you cannot steal a lot of money by saying that you are human and you are not. So this is a real problem. But say this, so this one is the use of AI to predict what is going on and to make decisions about it. Then fast forward a few years ago, all of a sudden people started talking about generative AI. So what is so interesting about generative AI is the fact that you can generate content. So you can generate text, you can generate images, you can generate music, you can generate code. And what does it mean, generate? It means that you are putting in an input, a request, a prompt, and out comes an answer that has the things that you want to have. Now, that is the very, very interesting if you can do it well. And then if you look at the mathematical point of view, and if anyone knows about statistics a little bit, a generative model is a statistical model of a joint probability distribution, P, X, and Y, on a given observable variable X and a target variable Y. This is what it does. This is generative AI. No more, no less. So it's a statistical generative model. And so being statistical, sometimes you get it, sometimes you don't get it. And when you don't get it, you get hallucination. And guess what? Because you're not sure that you are getting the right answer because you don't have enough quality data, or you are being given biased input or whatever other reason, and so you cannot be sure of what comes out. No. But generative AI has a lot of utilization. Why? Well, think about what we do all the time, right? For example, this morning I was looking at myself, I said, geez, for 1 hour, I've searched the network using Google Chrome, right? So I say, I don't know about, okay, Roland Garros tennis. Right? I wanted to know what the Italian tennis players were doing, okay? So if I had used ChatGPT, I say, tell me what the Italian players are, pah, comes up, all the statistics and everything. In this case, I had to find the site for Roland Garros, inside the Roland Garros, the table of play, and then inside that, I have to find the Italians, okay. So it's time consuming. The big use, in my view, of ChatGPT and all of that is about search. And search is a big business. Search. Why? Because the user interface is very natural and you search everywhere, right? So you have a complete entire network at your disposal to find answers to your prompt. And so that is going to be the single most used stuff because it's safe, fairly safe. It's not giving you worse than what you would do by hand searching the internet with Google prompts, right? So, okay, so that's the generative AI. And the interesting thing about the quality, I mean, I'm sure that all of you have tried ChatGPT, is amazingly good in terms of the language, the form of the language, right? And it's incredibly accurate, the English, not what is inside, the form. So it means that there is some magic trick that people use to be able to replicate natural language processing. And how did they do that? By using humongous large neural networks. Right? With 1 point, I mean, the latest are 15 trillion parameters. Forget about this 108 billion. Right? We are talking about trillion parameters. And how come? Well, because there are two big lines of research in natural language processing. One line is Noam Chomsky and all the clever people, right? And they were trying to figure out if there is a way in which you can construct sentences by first principle. So what is the language? So define language, define what is behind the language, and I'm going to generate language out of these models. Were they successful? Not so great, right? So they have grammar, syntax, semantics, semantic network, everything known to man. And they were able to replicate some language constructs, but nowhere near what we could do with large languages. The other line was about statistical model of language. And the statistical model of language is black box, right? So it's all based on the probability that a certain sentence is constructed by this word and this word and this word and this word. So it is a conditional probability, as we were saying before, generative, right? That a certain word would follow another word. So the first attempt natural language processing were quite interesting, but now we are at the point that is almost perfect. And why is that? Because people were able, by using these trillion parameters, etc., plus a mechanism that is called attention, that gives you the correlation of words, not only in the sentence itself, but in other parts of the same text. So now you have also the context. So context plus grammar rules and all of that equal really a very powerful method. And these are called transformers. These mechanisms that are able to correlate words in a complex text. And that was very revolutionary. Now, why did transformer get into the picture? Well, the first time the transformer was used, 2015, there is a famous paper that is called all you need is attention. Like all you need is love. Okay, take love away, and off you go. This is the way in which we form titles of fish, right? So, and the attention is this mechanism that correlates words across large span of text. Now, was it created for text and natural language processing? No. It was created for Go. Remember, like the famous game where the computer beat the world champion, Chebo, whatever his name was. And how did they do that? Using transform, trying to find correlation with moves that would follow a lot after what the game was taking place, right? So that was the revolution by itself. And this, the people who did it, say, do you think it's like chat, OpenAI, you know, were the people in UK, they were for DeepMind that was acquired by Google. And so now you may see that everywhere in artificial intelligence is pretty much dominated by the United States, yes and no, in the sense that the Cambridge company was acquired by a US company, of course, because they had a long eye to see that these guys were good. The same guys actually ended up, well, this is a large language model, we already said, so large language models are trained on the entire internet to text that you can find on the internet. The number of parameters is incredible. So we go from 1 trillion parameters of ChatGPT 4.0, 17.5 billion parameters by the Chinese, and boom. So everybody's running after more and more and more parameters. Why is that? Because the more parameters you have, the more span of the understanding of the text you can do. So the bigger is the span, the better is the language that comes out. Now, the content is a different story, because if I tell you, go into, I don't know, the French language domain, so everything that is in French, and then you train on everything that you see written in French, and then you ask, what is the better cuisine in the world? Guess what comes up? The French cuisine. Yeah. It's not true, obviously. Italian cuisine is better. But that's what you get, right? So the content depends on the set of data that you train your thing. Okay? And so the content is separate by the form. So the form is perfect. It's very difficult to fail this large language model, but the content, yes, you can fail it, and it's the hallucination issue. Okay, so let's look at AlphaFold 2. Now, this is really, really surprising. This one is the first time of the very old problem, which is protein folding problem. So try to figure out how a protein shapes the shape of the protein in 3 dimensions, given the sequence of compounds that generates a linear text. Right? So this has been an open problem for years and years and years. So people have tried to find solutions. They were okay in some cases, but nowhere near being able to discover the real structure. Well, with these transformers, these guys at that company, at DeepMind, were actually able to get the correct answer. It's amazingly accurate. So it's like 86% or better of all the proteins that have been given as a test case, they were able to find it. The next was like order of magnitude below. So this is really, really, really something totally, completely surprising and beautiful. And in fact, prediction, these guys are likely to win a Nobel Award for this discovery. Which is the user, okay, here it is, right? So there are 2 guys here, there's Jumper and Baker, are the 2 guys of the alpha or the protein folding. This is an award that was given to us. You see this lady on the right, she just got a Nobel Award in physics. And the guy on the far left, that's me. That's for design, so I'm not going to win a Nobel Award, but I predict that these 2 guys are going to win because of this AlphaFold. And if you look at it, you say, oh, fantastic. We have a neural network, basically, and the data, neural network magically will store everything. Not in the least. How many people? 1,000 people for 2 years. Again, they solve an unsolved problem, but if you look at the architecture, I mean, come on. How many people will be able to find that particular architecture without knowing the problem? So imagine this particular transformer idea and then multi-layer network and all that as a tool But tool has to be given in the hands of clever people. So otherwise, everybody else would find the protein folding, would solve a protein folding problem, which is not the case. So imagine a future where this is a tool. It's like, being able to do fast Fourier transform is a tool. But you have, as any tool, you have to use it in an intelligent way. So this is the frontier. How you put inside this stuff the knowledge of the problem at hand, right? So that's what, in my opinion, is going to be so important. So anyway, the other issue is that transparency. Now, suppose that you are, again, you want to make sure that whatever this model put out is not damaged, right? Or trying to figure out why it says that, I don't know, this guy is likely to be a killer, right? And in fact, some people in the United States have tried to use it that way. So in the police department, so they were looking at the faces, at past and so on, and predict that this guy is going to kill five. So, well, if they get it, and great. But if you have an innocent guy, not so great. So, what is the boundary between being able to predict if something bad happens with respect to something able to happen? So, this is all the theory of safe AI or explainable AI. And explainable AI is all about trying to figure out why you get the answer that you got. Now, how many parameters? Remember? Trillion, right? How can you find out what are the causes that gave out this answer? You have to figure out why all the 15 trillion parameters have been set in the value to which they have been set, right? Hopefully. So we got to find a way of structure the training and the architecture of the neural network in such a way that you can find the trace and say, oh, here is where the problem is. Because then you can also correct it. So it's a debugging also issue. So you want to not to continue on with this thing. So that's, as I say, is the important thing. And indeed, what we are doing in Berkeley is trying to do this explainable AI or better verifiable AI. And that is I talk way above my time. So I just want to give you a quick thing, and is again the autonomous vehicle or in general the design problem, you have specification. I want to do verification on your design, which means is what I design compliant to what I specify. And then the synthesis thing, how can I make my design do what I specify? So this is all what we do in cyber physical system design. Now the problem with autonomous system, in particular AI-driven autonomous system, is that you get a system S that you are designing. You have an environment that is where this design is living. So if you are designing an autonomous car, the environment is going to be the road where you are. And then there are specifications that, of course, you want to make sure that the car doesn't crash, for example. And so does the combination of the system and the environment satisfy my specification? Now, the environment can be pretty crazy, right? That's the problem. We can have this guy, which is actually a traffic cop in UK, which is actually dancing in the street. Is one of the thing that they do to entertain tourists, right? If you go to Rome, you have something similar. So you have a cop that does all these kind of nice moves. But imagine the artificial intelligence that is trying to figure out what the heck is this guy, right? And what is he doing? Well, okay, that's the environment. Now, and then you can have a race, right? We just finished the Giro d'Italia, and it's going to be the Tour de France. And you do have a race that goes by normal roads, and then you have to figure out what the heck is this swarm of people with bicycles doing, right? So that's again on the interesting scenarios. And then you have a poor car which is got inside a neural network. Hallelujah, right? So poor neural network is trying to figure out what is going on. And so is there a way in which we can verify this stuff? And so that's a problem. Now, since there are two ways in which you can verify. You You can prove that everything is correct, but we say before, this is an approximation technique, so there is no proof. And so what we would like to do is to try to find counterexamples as much as possible, and then correct the things where this thing doesn't work. And that is the verification-based, simulation-based verification, which means that you simulate the behavior. Why simulate? Because simulate, you are living in an artificial environment, so you can create all kinds of weird situations that in the real world you're not going to see. Okay, so, and you can focus on things that are very rare. And that is the value of a synthetic analysis on data rather than measuring what happens in real situations, because the bad examples are going to be so small, so few, that it's almost impossible to figure out. So what we have done is that we built an environment, synthetic environment, where you can create all kinds of trade situations. And then you can see whether your system is going to verify suspicion or not. If not, then you focus on that corner and you try to find the cause why this is not working correctly, and you correct it. Right? So that's a way in which we can eliminate a lot of testing on real roads by and correct all this AI kind of driven decision. Now, mind you, 99% of the autonomous cars are using AI models to recognize the environment, not take decision. As often the decision is taken by using more deterministic algorithms than this. Okay, so that's something that I just give you as a food for thoughts, and then the last thing I want to leave you with is that can we combine these statistical techniques with physics-driven insight into the model? And that is the latest thing that we are working on, is like physics-inspired machine learning. Right? So that at least the core of the computation has physical meaning, and so you don't run the risk of hallucinating too much. Okay, that's it. So thank you very much for your.
Okay, thank you very much. We have time for some questions and comments.
Yeah.
He's a statistician, that's why.
I met him before.
Questions. First comment about the claim Panathinaikos where there was 3 positive probability that Panathinaikos will win, so it was probable. Less, maybe less, but still probable. And the second, I don't understand about this like autonomous vehicle. What is the cost function?
Yeah.
What is the loss function? How and look, I mean, all these are trillions of weights and parameters. I guess there are also some kind of restrictions, right? I mean, it's so fast, otherwise the problem might not even be defined. So I just want your comment. Okay? I don't understand that.
Well, I mean, the cost function is always, you know, remember that in the autonomous vehicle there are several components, right? So one is recognition, image recognition, and that is neural networks all the way, trying to figure out if that is a car, that is a person, that is a tree, right? So image recognition. So, and you can fool that, right? The big problem on that is the fact that it can be fooled. So if there is a bad guy who wants to cause an accident, it's going to show you something in front of the car that is going to completely confuse that model. Then there is the decision-making model, and the decision-making model is more complicated. So there is one which is about the mechanics of the car. So, I mean, if you turn the wheel, then this car is going to go there and so on. So now you have a decision to make, like, for example, do I stop or I continue? Right? And that is based on the recognition. recognition of the image. So it's still almost a classical decision-making problem. So the real crux of the matter in terms of machine learning is on the recognition piece. And so now, in terms of the cost function, when you the key cost function is adding an axis. So this is priority one. Priority two is that you want to have the smoothest ride that you can, so not stop and go. But, you know, this stop and go was a problem originally. And if you look at, for example, Tesla on a freeway, and you let autonomous driving going, it's amazingly smooth. I mean, it's incredible. It's better than any human driver that I've seen. But of course, if you get, for example, in Silicon Valley, you get all kinds of crazy stuff. So you get the guy who reads the newspaper while he's driving, real, or the lady who's actually real, I saw it with my eyes, with painting a toenail. So I was putting foot on the driving wheel, and when I went by, I said, oh my God. So, okay, so this is, you know, slightly difficult to guess, right? But again, in the end, maybe that image recognition is going to be able to figure this out. But for sure, you cannot avoid 100% crash, right? So the cost function, as you said, is a reinforcement learning based. And so the cost function is that you recognize the right thing, you don't have a crash, and your ride is smooth, and you don't cause other problems. But
other questions, comments?
How do we add physics to the image recognition?
hey, okay. So back to the future. All right. So let's go back to the 80s, no, 70s. SPICE. I don't know how many of you know what SPICE is, but it's a program for simulating integrated systems. So the first version of SPICE was 1975, and simulation, you need models, and you need equation solvers. That's it. So a simulator is based on these two principles. The simulation model is a model, right? So I could use, and what are the components? So it's the transistors, right? So you need to have the equation that connects the input and the output of a transistor. Now, physics we know, so we know how the transistor more or less behaves, but there are second order effects that are caused by tunneling effect, the electrons that interact and do whatever they want, right? So anyway, and so we developed three models. Model one was a simple one for students, it was really simple. And we did it just to show how to leverage the characteristic of a transistor. Now, I wouldn't recommend to use that to figure out if the manufactured chip is going to do what the simulator would predict. Then it was level 3, that was fully physical to the field, right? With all kind of second order effects added. And then there was level 2. Level 2 is in between. It's called semi-empirical model. And why it was called semi-empirical model? It had a physics, but some second order effect in the light, plus what we call a fudge factor. What was the fudge factor? Was a polynomial with positive and negative exponents. And this polynomial was an approximating function. And so we would find the coefficient of this polynomial by doing measurements. So that was like a neural network, except we use a polynomial, right? That the core of the physics plus this. Guess what? The SPICE level 2 model was much more accurate than level 3. So there is something to be said about mixing statistical and deterministic model. Because the statistical model can take into consideration things that you don't even know the equation for. But you want to keep things in shape because the first order phenomena are predominant. So you get the second order effect by doing that. So that's one thing that we are looking at. To generalize, so can we say something about this? And in fact, the last slide, I have some equations just for the panel in which we mix the two. And we try to demonstrate that this way The bound is going to be given by physics.
Okay, one last question and then we wrap it up.
Thank you for the presentation. My question is regarding balancing data set. For example, if you have any type of physical system, it usually spends most of its lifetime in a steady state condition or a cluster of what is considered steady state conditions. So if you are going to use faulty or abnormal data in your data set, you have to decide how much of the data is going to be represented by this abnormal data. If you introduce too much of this abnormal data, you are biasing your model into seeing things that don't exist and probably increasing your false positives. If you represent all the data in a more realistic type of manner, for example, with the frequency of occurrence in the real world, you probably underplay their importance in identifying them. So what's a good way to balancing this?
There is no good way, but there is engineering sense, right? So in general, it's always the problem of curating the data, right? Because the data 99 times out of 100 do contain faults, right? So they are not real. Because of the sensor, it's broken, because of the fact that you are considering effects that don't matter and all that kind of stuff, right? So the curation of data, unfortunately, it is a very complex stuff. So it is a rare occurrences. Then you can have an out of distribution mode in which you are analyzing what doesn't jive with the regular model, and then you focus on that, and you have a human intervention to verify whether this is a real condition or not. This is what people do. By the way, also when the neural network hallucinates, then you have real people looking at the data and say, why did they hallucinate? So you have cohorts of people behind in OpenAI and all that are looking at the answers and try to correct it. Because there is no other way. Because again, the broken data is broken. So you cannot follow it, but how do you know it is broken? So you have to ask someone who's going to judge it.
Okay, well, thank you very much. Thank you very much, Alberto. Thank you, everybody, for attending.
Thank you. Exactly.